Hello, my name is Micah Swann. I'm a PhD candidate at UC Davis in the Department of Civil and Environmental Engineering, advised by Dr. Jeffrey Schlato. I conduct applied lake research using high-frequency measurements of temperature and dissolved oxygen in conjunction with numerical modeling to better understand how interactions between hydrodynamics and biogeochemistry influence aquatic ecosystem health in lakes across North and South America. Today, I'll be talking about the monitoring and modeling program that I've been working on to better understand the sources of nutrients fueling harmful algal blooms in California's oldest and largest freshwater lake, Clear Lake. Clear Lake is located approximately 2 hours north of San Francisco and is a vital natural, economic, and cultural resource for shoreline residents, and in particular, the native tribal communities who've lived in balance with the lake for generations. However, the course of the 20th century, the lake has been increasingly plagued by harmful blooms of cyanobacteria each summer that cover the lake with scum and produce neurotoxins, which can be harmful for humans and pets if ingested, reduce aquatic biodiversity, and result in increased water treatment costs. These blooms are so frequent due to the excessive amount of nutrients, and particularly phosphorus, that's entering into the lake. Nutrients can come from external sources in the watershed, such as agricultural or urban areas, or from the bottom of the lake itself when dissolved oxygen concentrations are low. To better guide future lake restoration projects, my research has had two objectives. First, I aim to quantify the relative contribution of both external watershed phosphorus sources and internal nutrient sources to the lake's overall phosphorus budget. And secondly, I've aimed to investigate how interannual variability in climate and lake hydrodynamics influence changes in the severity of cyanobacteria blooms in Clear Lake from one summer to the next. To answer these two questions, I've used a range of techniques at varying degrees of temporal and spatial resolution to provide a holistic view of how physical lake processes impact nutrient and cyanobacteria concentrations. I used moored underwater high-frequency loggers to observe how the lake's thermal structure and oxygen concentrations change seasonally. I collected grab samples of water from various locations and depths to analyze how nutrient concentrations change through time. I conducted lab incubation to determine the amount of nutrients being released from sediments under varying temperature and oxygen conditions. And I used remote sensing tools to quantify the lake-wide severity of cyanobacteria blooms. Using the experimentally determined sediment nutrient release rates from the lab incubations and the continuous measurements of oxygen and temperature at the bottom of the lake, I was able to quantify the internal load through the entire year and determine that the lake itself, not its watershed, was the primary source of nutrients to the lake. Furthermore, we found a somewhat counterintuitive result that there was greater loading during dry years when there was minimal external loading compared to wet years when streams conveyed a larger mass of phosphorus into the system. The reason for this is that the total load of nutrients and ultimately the severity of the summer cyanobacteria bloom season is primarily regulated by how long the bottom of the lake remains low in oxygen and the subsequent amount of nutrients released from sediment into the water column. For the first 2 years of the study, low oxygen periods lasted for only a few days at a time, while in 2021, there were almost 3 consecutive weeks in the summer where oxygen at the lake bed was near zero, resulting in the most severe cyanobacteria season on record. I hope that these findings will motivate regulators to focus on mitigating in-lake nutrient sources in addition to the watershed restoration projects that have been historically conducted. Thank you to the ARCS Foundation for your support. Your generosity has allowed me to pursue my passion of conducting applied research to better protect lakes for future generations.